Special relativity theory. A critical review of Einstein's derivation of Lorentz transformation. Part 4.1. A deeper insight into the derivation of Lorentz transformation by Einstein, by Hossein Ahari. Lorentz transformation. As I mentioned in previous sections, the Lorentz transformation is the core of Einstein's special theory of relativity. It is supposed to translate the quantities of time and space between two inertial systems. I have already presented some obvious contradictions to this theory. We would continue our investigation by focusing on the mathematical method used by Einstein, then I'd introduce a new and more understandable approach to deriving of the Lorentz transformation. But first, a short summary of what we discussed in previous parts. A short summary of previous parts. Part 1. Contradictions by time dilation are not removed by using complete Lorentz transformation instead of the simple T equals gamma times T prime equation, as Dr. Don Lincoln says. A real-time dilation would mean different ticking rates of clocks at different points of a long-moving train. Part 2. By quoting from his own book, we showed that there are contradictory statements about constancy of light velocity in his own writings. He wrote, now in reality considered with reference to the railway embankment, he is hastening towards the beam of light coming from B, whilst he is riding on ahead of the beam of light coming from A. Hence the observer will see the beam of light emitted from B earlier than he will see that emitted from A. A short summary of previous parts. Part 3. Using an example I showed, despite the complete equality of two observers in inertial systems K and K', they would measure different lengths for the unique distance between K and K' at a certain instant of time, for example, T equals 5, according to the first equation of Lorentz transformation. With V equals 0.6 c, we get gamma equals 1.25, and applying these values in Lorentz transformation equations result in two different values for a unique distance of two systems K and K'. One, we assume observer to be in K. In the origin of K', x prime equals 0, from the first equation for T equals 5, x prime equals 0, x equals 3c, and T prime equals 4. 2. We assume observer to be in K'. In the origin of K, x equals 0. So for T equals 5, distance of K from K', x prime equals 3.75 c and T prime equals 6.25. But according to the relativity, these two distances are to be the same, and the clocks in two systems must show the same time. Because the two systems are not superior to each other. The mentioned contradictions show that either some postulates are wrong or the equations are to be interpreted differently. Investigation of the underlying causes of the controversial interpretations. A deeper insight into SRT and Einstein's mathematically incorrect derivation of Lorentz transformation.
Appendix 1. Simple derivation of the Lorentz transformation, supplementary to section 11. For the relative orientation of the coordinate systems indicated in figure 2, the x-axis of both systems permanently coincide. In the present case, we can divide the problem into parts by considering first only events which are localized on the x-axis. Any such event is represented with respect to the coordinate system K by the abscissa x and the time t, and with respect to the system K' by the abscissa x' and the time t'. We require to find x' and t' when x and t are given. A light signal, which is proceeding along the positive axis of x, is transmitted according to the equation x equals c times t, or x minus c times t equals 0. Since the same light signal has to be transmitted relative to k prime with the velocity c, the propagation relative to the system k prime will be represented by the analogous formula.
X prime minus c times t prime equals 0. Those space-time points, events, which satisfy 1, must also satisfy 2. Obviously, this will be the case when the relation x prime minus c times t prime equals lambda times the quantity x minus c times t is fulfilled in general, where lambda indicates a constant. 4. According to 3. The disappearance of x minus c times t involves the disappearance of x prime minus c times t prime. If we apply quite similar considerations to light rays, which are being transmitted along the negative x-axis, we obtain the condition x prime plus c times t prime equals mu times quantity x plus c times t. By adding or subtracting equations 3 and 4 and introducing for convenience the constants a and b in place of the constants a lambda and mu, where a equals quantity lambda plus mu over 2 and b equals quantity lambda minus mu over 2. We obtain the equations x prime equals a times x minus b times c times t prime equals a times c times t minus b times x. We should thus have the solution of our problem if the constants a and b were known. These result from the following discussion. For the origin of k prime we have permanently x prime equals 0, and hence according to the first of the equations, 5. X equals b times c over b times t. If we call v the velocity with which the origin of k prime is moving relative to k, we then have v equals b times c over a. The same value v can be obtained from equations 5. If we calculate the velocity of another point of k prime relative to k, or the velocity directed towards the negative x-axis of a point of k with respect to k prime. In short, we can designate v as the relative velocity of the two systems. Furthermore, the principle of relativity teaches us that, as judged from k, the length of a unit measuring rod which is at rest with reference to k prime must be exactly the same as the length, as judged from k prime, of a unit measuring rod which is at rest relative to k. In order to see how the points of the x prime axis appear as viewed from k, we only require to take a snapshot of k prime from k. This means that we have to insert a particular value of t, time of k, e.g. t equals 0. For this value of t, we then obtain from the first of the equations, 5. X prime equals a times x. 2 points of the x prime axis which are separated by the distance delta at x prime equals 1. When measured in the k prime system are thus separated in our instantaneous photograph by the distance delta at x equals 1 over a. Analyzing of Einstein's derivation. In page 139 line 12, Einstein writes, a light signal, which is proceeding along the positive axis of x, is transmitted according to the equation x equals c times t or x minus c times t equals 0. Since the light signal has to be transmitted relative to k prime, with the velocity c, the propagation relative to the system k prime will be represented by the analogous formula x prime minus c times t prime equals 0. Those space-time points, events, which satisfy 1, must also satisfy 2. Obviously, this will be the case when the relation x prime minus c times t prime equals lambda times the quantity x minus c times t is fulfilled in general. 1. The cause and effect relationship is misrepresented. It has to be written, obviously, when 1 and 2 are fulfilled, the relation 3 is satisfied too. Confusion is the result of Einstein's incorrect mathematical methods and faulty reasoning. Page 140. line 10. If we apply the quite similar considerations to the light rays being transmitted along the negative x-axis, we obtain the condition x prime plus c times t prime equals mu times the quantity x plus c times t. 2. It is only 0 equals mu times 0. As mentioned before, this is the result of our postulate of constancy of the light velocity and not a condition. By adding and subtracting 3 and 4, we obtain equations 5. X prime equals a times x minus b times c times t. T prime equals a times c times t minus b times x. 3. Adding or subtracting two functions which do not have a common domain is mathematically wrong. Domain of 3 contains all x equal or greater than 0, and the domain of 4 is all x equal or smaller than 0. The only common valid point is x equals x prime equals 0. 4. The whole math operations for obtaining 5 used by Einstein are unnecessary and superfluous stories. Because it is obvious from x equals c times t and x prime equals c times t prime. X over t equals x prime over t prime. We can write this in form q times x over q times t equals x prime over t prime, and come on, x prime equals q times x, t prime equals q times t, when q is assumed to be a constant. If we assume q as subtraction of two other constants a and b, simply we get from x prime equals q times x, x equals c times t, x prime equals c times t prime, the equations 5, q equals a minus b, then x prime equals a times x minus b times x, or x prime equals a times x minus b times c times t, or substituting x prime with c times t prime and x with c times t prime equals a times c times t minus b times x. Have you ever believed that equations 5 is nothing more than x prime equals q times x, or t prime equals q times t, when you split q to q equals a minus b and apply x equals c times t and x prime equals c times t prime? It is clear, if the light velocity should be maintained constant, then we should have x prime equals q times x and t prime equals q times t. Only one of x or x prime refers to a real length. The second paragraph on page 141 is important, not only because of the derivation of the Lorentz transform, but also to get an idea of what to look for. In line 6 of this paragraph, we read, in order to see how the points of the x prime axis appear as viewed from K, we only require to take a snapshot of K prime from K. This means that we have to insert a particular value of t, time of K, e.g. t equals 0. This means that setting t equals 0 results in the value of the scene length, x, of a real rod with the real length of x prime, which is assessed from K at time t equals 0. So, in equations 1 of x or x prime is related to an imaginary photograph of a real length, e.g. the measuring rod. Einstein simply forgets it and writes, the rigid rod is thus shorter when in motion than when at rest. In Lorentz transformation, if observer is in K, then x, t are only the viewed values and x prime, t prime, the real ones, and vice versa. The root of confusion is in Einstein's own contradictory statements. We showed earlier, Einstein has written by derivation of Lorentz transformation on page 141. In order to see how the points of the x prime axis appear as viewed from K, we only require to take a snapshot of K prime from K. This means that we have to insert a particular value of t time of K, e.g. t equals 0. But contrary to this statement about how the points of the x prime axis appear as viewed from K, on page 42, he changes the appearance to the real length. Chapter 12. the behavior of measuring rods and clocks in motion. I place a meter rod in the x' axis of K' in such a manner that one end, the beginning, coincides with the point x' equals 0, whilst the other end, the end of the rod, coincides with the point x' equals 1. What is the length of the meter rod relatively to the system K? In order to learn this, we need only ask where the beginning of the rod and the end of the rod lie with respect to K at a particular time t of the system K. What is the length of the meter rod relatively to the system K? And at the end of this page, the rigid rod is thus shorter when in motion than when at rest. The difference is the difference between image of a rod and the real rod. The point of deviation. In this way it seems that we have been able to reach the point of deviation. As long as Einstein seeks to achieve the Lorentz transform using the principles of relativity, he speaks of the equality of the images seen by the two observers. But after derivation of the Lorentz transform, he replaces the same image of the rod with the real rod, claiming that the length of the rod becomes shorter in the direction of motion. The absurdity of such a claim becomes clearer when three systems are considered instead of two, and if there are different relative velocities, each bar must have two different lengths at the same time. To be continued.